Okay, we'll get started. We talked about capacitors, and we said essentially it's going to be two parallel conducting plates here, or some sort of insulator in between. Defining the equation for capacitance is coulombs per volt. That's something we'll need to memorize. We'll be using that quite a bit. Also, if we know physical dimensions, capacitance is going to be the permittivity of free space times the relative permittivity of the dielectric times the area divided by the distance. So if we want to get a larger capacitor, we could increase the physical size. So that would increase that maybe 100% on that. But if we want to do it more, then we are going to be ending up with something that's really unwieldy. So to be able to get this thing packaged better, let's assume that we'll put a dielectric that's flexible inside that, something like a mylar plastic, it'll look like saran wrap, that thing. And then if we use, rather than a rigid metal, if you use like tin foil on that, then you can just take this and sort of coil it up and end up with a little tube. And then encapsulate that to give us some mechanical strength. And that's going to be a common way in which we can make capacitors, rather than having the parallel plates, do that encapsulation. This is a capacitor that is constructed in that manner. You've had capacitors like this on the CEEN bot, so a little out of focus. So this is the way in which that one was made. Now this is going to be a capacitor. This specific type is going to have an electrolyte. It's sort of a moist material between the plates and that saturates the dielectric on this. So it's got an electrolyte in it. The type of capacitor then is referred to as an electrolytic capacitor. With the electrolytic capacitor, there's a polarity associated with it. So if you remember when you're doing your soldering with that black, either black or blue, depending on which kit you had to make sure you had the leads correct on that. So you need to have the plus side going to the plus side of the battery, minus side going to the minus side of the battery. Once this voltage is applied to this, the electrolyte forms an insulation on that. If you were to put the battery in the opposite way, it's not going to work. It's actually going to conduct, so it has to go in the correct orientation. If you put it the wrong direction and you have the battery applied, then current's going to flow through it. It's got resistance. It's going to overheat. It's got a sealed thing, so like a pressure cooker, it's probably going to explode. So that's a common failure mode on capacitors, is to have them explode. A couple of years ago, we had some students, Austin Steiner was one of them, that in the lab decided let's do the experiment and videotape, so they videotaped applying voltage and watched them explode. I assume he still has that, and I'm going to try to resurrect that so you can see what it does look like when it does explode. But they'll explode with a bang, and things fly all over. So if you decide to do this on your own, I don't recommend it. Wear safety glasses or stay a fair distance away from that. If we have a alternating voltage supply, and we haven't talked about those in this class, alternating would be like the 110 volts we have coming out of the outlets. What's going to happen on that is that half of the time you'll have a positive voltage, the other half of the time it's going to be negative. So if we got this set up like this, for this cycle, we're working fine. This cycle, get the reverse on that, and that's what it's going to cause the damage. So the electrolytic on AC by itself is not going to work. But there are applications where you do need to have a capacitor similar to an electrolytic on motors. So the motor start capacitor is necessary, and you won't know how this works yet. Later on you'll get it figured out. But with the capacitor in a circuit, you can change the phase of the signal coming in. So by changing the phase of it on your starter, on the motor, it then gives it starting torque. Once it gets going, you don't need that, and then it will have a centrifugal switch in there that switches it up. But you do need to have this capacitor on the motor to get the thing going. So this is not going to work. So what they do for motor start capacitors, they'll put two of them in series. We'll have this one with this polarity, the other one the opposite polarity. So on the plus cycle, this works as a capacitance. This one is just a small resistive component. On the negative part, this one gives you your capacitance, and then this one is like the short circuit. So that's going to be a typical way in which those will operate. The advantage of an electrolytic capacitor is that you get a lot of capacitance in a small volume. Well, we know that the units on capacitance are going to be farads, but you're probably never going to use a 1 farad capacitor. It's just a huge device. You don't need that. Typical values we'll be working with ten times 10 to the minus 12. 10 to the minus 12 is pico. So a 10 picofarad capacitor is on the real small end. You may see them down to 1 picofarad, but probably not. So a 10 picofarad is still going to be a really small capacitor. Typical ones we're going to be working with and what we're doing uh, 0.01 micro is 10 to the minus 6 microfarad capacitor up to maybe 100 microfarad capacitors. The one that I've got on this screen there is a 10 microfarad capacitor. And if you get really large ones, maybe 10,000 microfarads.
How big are they?
I'll show you in a minute. Okay. So anyway, the ones we'll be having most of the time in this class, and most of them are going to be running this in the middle area here. They do make capacitors that are in the farad range. It uses a different technique, and they're referred to as supercapacitors. They haven't been around all that long. But they're usually not used in electronic type of applications. They're going to be used quite often for storing charge for a long period of time. So as you're changing batteries on a electronic device, you could have this supercapacitor that would hold all that charge on there, so it powers the device while you're switching out the batteries. And we'll see how that's working as we get more applications on that. So anyway, this is going to be the electrolytic. The purpose then on most capacitors that's we're going to be using them is to get rid of variations in voltages. So your power supply, you want it to be 12 volts, you don't want it to be 12 bouncing up and down. So capacitors are going to help even that out. As an example, you can sort of consider the capacitor like a big water tower. It's going to store charge. So the more charge we store in it, that'll be the larger capacitance. The voltage is not, as you start taking charge out of there, the voltage isn't going to change that much because you get a lot of charge stored in there. So the big water tower prevents you from having fluctuations in water pressure in your water system. Capacitors will help maintain constant voltage on your system in light of different current draws you'll have on that circuit. This capacitor here is a motor start capacitor. It's a really large one. Most of you are going to be seeing would be smaller, more in this size range. But this one will work up at 230 volts, and I think it's about 50 microfarads. I think it's 50 microfarads, so it's a big, heavy thing. And it's got the two of them, you know, like back to back in there, so you don't have to have a separate one. But that is a motor start capacitor. This capacitor is an electrolytic, and you can just even see by the shape it, you know, it's got the windings going around in it. This came out of an old IBM computer that we disassembled a long time ago. But this one's a 25,000 microfarad device, and it'll work up to 75 volts.
These are all, they all have ceramic in them?
No, those don't have, those have electrolytes. Those aren't ceramic ones.
Patches are pretty bad.
Yes, they do. That's a common thing that does go bad on electronic devices are the electrolytic capacitor. So that's, a repairman, that's probably going to be one of the first things to look for, because especially if it's got a breakdown, you can see the discoloration, the bubbling of the paint, things like that. Especially if it's a power supply problem, that's probably what the difficulty is. Okay, we've mentioned that ceramic is a real good material. It's got a relative permittivity of 7,500. This would be a ceramic capacitor. These don't have a polarization associated with it. They work with AC, DC, it doesn't matter. But they typically only go up to about 10.01 microfarads, or maybe up to 0.1 microfarad, but you won't see them much larger than that.
We noticed that the orientation didn't matter with those ones.
That's
Well,
right.
in lab.
Because they're made differently. Okay, this one was made by Western Electric, which you've never heard of, but I used to work there. It's made of polystyrene. We didn't make them here in Omaha. But you can sort of see that it's probably had a flat piece of paper in there, and they just wound around that to get the shape that they've got. Different materials give you different electrical properties. The electrolytics, they give you a lot of capacitance per volume, but they have a higher impedance. They don't work well much above your 60 cycle, so they're going to be for low frequency. Ceramics, those will work at higher frequencies. Polystyrene work at higher frequencies, and they're also a lot more temperature independent than some of the other ones. Yes.
Are supercapacitors what they use in like regenerative braking in cars and stuff like that for hybrids?
One of the, I haven't researched that, but I've heard them talk about the supercapacitors in the cars. One of the problems with regenerative braking is you're using the brakes and the motors as generators, and then you're recharging the batteries. Well, the problem is the energy is coming off of that generator faster than what the batteries can absorb it. So I've heard of them using the super caps to be able to store it temporarily while it's got a chance then to work out, sort of like a watershed, a dam on the thing. And I don't know if the current version of electric hybrid cars use super caps or not, but I read about it in an article that it's a possibility.
It'd be smart.
So that
It'd be smart if they did it that way, don't you think?
now there's a lot of cost involved in it too, to get enough capacitance to hold all that. So it's all finance, it's all, you know, cost analysis trade-off.